Welcome everyone to the working group meeting. Today we have basically 2 points on the agenda. Let me quickly share my agenda before we start. So the first point would be a presentation by Matteo. Matteo is also with us in the Convince project, which was kind of the main point where we decided to start the working group. And he will talk a bit about his previous work on how to execute skill-based robotic behaviors. I guess, Matteo, would it be okay if you speak for roughly 20 minutes and then we take 5 minutes for questions? Okay, then we have another half an hour to discuss this rep proposal that I made. I've seen Davide. Thank you very much for the pull request already. But I guess there are also some points that we can discuss live while we are here. But for now, I guess, please, Matteo, the stage is yours.
So, hello everyone. I'm Matteo Morelli from CEA. I'm a research engineer from CEA in France. So today I will talk to you about the work we are currently doing at CEA, so namely a tooled approach to programming and execution of skill-based robotic behaviors. So there are 2 main parts in this talk. Yeah, sorry. You see the screen, right? Okay, so before starting going to the slides, I wanted just to say that there are 2 main parts in this talk. So the first is the software architecture that we are developing for executing skill-based robotic behaviors, which is called Squidly. It's a name that we found interesting because it reminds the intelligence of this animal, the squid, which is very much appropriated for deliberation and intelligent behaviors. And then the tooled approach that comes with an approach mostly based on low-code programming. And then I will give you some perspective on the ongoing work that we are doing and telling also something about future work. So let's start with the software architecture that I've just mentioned before. So the main motivations for developing this software architecture for executing skill-based behaviors. You see a video here. We have done this at CEA. This is a challenge that we did. Basically, it was I skipped this part at least for the moment. It was a system setup with a vision system, a robot arm, and some gear units that comes from a NIST challenge. And the robot basically has to do the task that you are seeing right now. So pick every part of the gear assembly from the assembly tray and putting it to the deposit tray. So to construct the full gear. So here we have a lot of skill in the system that must be integrated. We had 4 teams at CEA, very much experts in their field of expertise. So computer vision, robot control, digital twin for motion planning. So what was needed was an architecture capable of orchestrating all these skills. And there was also a part related to human-machine interface, so that when something went wrong, So like, for example, a part in the deposit tray that is not found, like here. For example, we are asking the robot to perform to grasp a kind of gear that is not available. Then we needed to interact with the human-machine interface, and also a motion capture device that was able to recognize the operational zone of the operator to suggest the robot the next action to do. So given that in the previous case, the operator did the work close to the deposit tray, so the system was suggesting to the robot to restart doing the task again. So the robot is going to select the gear and continue the assembly. And here the other way was that the human operator could do the task by itself, and so the system was able to infer that the next good move for the robot was continuing with the next operation, because the other one was already been done by the user. So all this to say that we need the integration of a lot of skill capabilities from complex system, but even more complex than this, because we had projects where the use case involved multi-robot setup. This is the use case that we are doing right now in Convince. There is a robot arm and there is a mobile platform, and the mobile robot has to fetch blocks and put them in a kill card. So I don't go into the detail here, but just to understand the complexity of the system. There is a vision system again. So we did the previous experience, the previous use case in a dual arm setup. So the need of orchestrating the two arms was quite demanding. And we also have used this architecture for not only for, I mean, robot in the traditional sense like ARM and mobile platform, but also agents like drones, for example, that have used, in our case, was behavior tree based reactive navigation strategies to avoid essentially obstacles for when doing some navigation and then landing to a rover. But we also have used them to coordinate agents in simulation scenarios, like in autonomous driving, where we wanted to verify, for example, scenarios where the car has to avoid the pedestrian, and we wanted to coordinate the movement of the different agents in such a way that we could be able to reproduce a dangerous situation, so exactly to see if the driving policy of the car was able to work well, and so on. So all this is our motivation. So essentially we deal with complex systems of different sides and different number of agents with different components and so on. We found this skill abstraction as the capabilities that the system components can expose as a good way to orchestrate the different agents in the system. And we wanted to develop an architecture, a runtime architecture that could be scalable and could be capable of integrating all these different components. So, of course, based on ROS, because it's the standard, the technology that we use in our projects. So, essentially, our architecture is component-oriented, of course, and we have, as I said before, components that provides the real algorithms like computer vision, robot control, but also reinforcement learning, possibly, or we have digital twin that can essentially represent the geometrical data of the scene and all the information that we have in the scene at the geometrical level. And then all these components have a life cycle, and they can expose what we call, for example, atomic skill. So the atomic skill is the single capability that is immediately related to the algorithm. So the atomic skill, in this case, for example, find object, is implemented by a computer vision algorithm. But, for example, follow trajectory is another example of atomic skill that can be implemented by two entities, the robot control and the digital twin in simulation. And they use in our architecture the same API so that we can map it easily to the different components. Then we have a bunch of other possible atomic skills, and these atomic skills can be composed to essentially implement what we call composite skills for implementing more complex functionality, more complex in the sense that is a functionality with a logic, that can be a sequencing of a set of skills and or other strategies with different complexity. And then, of course, all of this can be composed again to provide even more complex functionality, more and more complex functionality, until we essentially define a task based on all these skills that is executed by a task plan sequencer. So what I didn't mention here is that the blue cylinders here are part of a shared knowledge base that we foresee in our architecture. The knowledge base has at the lowest level the geometrical information that comes from the digital twin, that is the entity that is fed with the data from the perception system, and can provide the object poses, the robot configuration, and so on. But then we have also other kinds of knowledge, like the static parameters for configuring the parameterization of the skills and the task that the robot must execute. So if we go in a little bit more close view of what the atomic skill is, we have some naming convention in our architecture for the skills in terms of device, domain, and the skill name. These are implemented using the action pattern in ROS. The binding that you see here in the API can be C++ or Python calls, or just a binding to another middleware. So essentially, what our atomic skill server resembles is a life cycle node, so with all the operations for configuration, etc., that can expose primitive skills as action servers, but also other data or computation part as services, for example, to evaluate conditions, etc., but also publish subscribers for data sharing when the different components have to interact among them to realize a complex functionality, or to signal some error or things like that. For what concern the composite skill, on the other hand, we had the behavior executor abstraction. Essentially, a composite skill, as I said before, can be implemented with a composition of atomic, but also other composite skills. And we implemented the architecture in such a way that can be, the behavior executor can follow generic behavior specification, like, for example, behavior trees or even final state machines. So we have some class hierarchy that is a little bit schematized here. So essentially, a behavior executor is a life cycle node in ROS, and the user has to implement just a couple of functions to basically be able to instantiate a behavior executor. So get name, which is essentially a method to indicate the name of the action, the name of the skills that the behavior executor is going to implement, and also other function, and also the bind policy parameters, because there is a need to bind essentially the goal that the skill is going to receive with the internal execution context of the skill itself, to essentially execute to remap the argument for reuse in the skill logics. So, for example, like in behavior tree, we have port remappings and blackboard items. So, from a point of view of the implementation, we have the executor context, which is an abstract class, which for now is specialized by the behavior tree execution context, and in the future we are starting now to deal with also supporting final state machines. So the most of the effort for now was essentially in implementing this architecture to support behavior tree based behavior execution. So essentially, a composite skill, to summarize, is a behavior executor. A behavior executor that has a concrete instance of an execution context. In our case, as I said, for now we all implement behavior tree compatible execution context. So this context means a data structure that embeds, for example, an execution engine, then other specific functionalities like a contextual representation of the information. For example, in the behavior tree, there is the blackboard, and then some generic methods to be able to run the logic. So, for example, to be able to run the process of the whole logic in the behavioral specification. So yeah, so we provide some. Of course, another part of the behavior executor is the action server, which is capable of reacting to execution requests. So essentially, the behavior executor is exposing a composite skill, for example, a move to skill. So when it receives, it needs to have an action server, of course, to be able to react to request to execute the composite skill. Then we provide some implementation of this in terms of task plan executor, but also other example instantiation, but I don't want to go into much detail here right now. So for what concerns the implementation, this is a point that I think could be interesting for this working group. So we didn't reinvent the wheel to re-implement all of this. We start with the great work done in Navigation 2. Navigation 2 provides for our BT executor context that I just described right now, a lot of code that is needed. So we got inspired very much from this. We just tried to extract what was the navigation to agnostic parts for executing behavior tree, to have a framework that could execute behavior trees in general, so without being too much bound to navigation to concept, etc. So, for example, the behavior tree engine class, it was great because it was a wrapper wrapping nicely behavior tree CPP. Its machinery, so the factory, the XML parsing, the nodes with the plugins, etc. And it only depends on RCL CPP, so it's perfectly reusable in any other context and not only in navigation too. So with robot arms, it's perfect. With drones, it's perfect, etc. Then there is the BT action server class, still in the package navigation to behavior tree, which gave us an excellent inspiration for the structure of the context. So the way in which the behavior tree engine is embedded, and many other things. So what we did differently was the way in which some parameters are passed to the node. So in navigation 2, they adopt an approach which exchanges ROS node through blackboards, which is their way to be able to make all the machinery work for composite skills. But also following the advice in some discussion by Davide, we follow a different strategy, and we use the additional arguments pattern of behavior tree CPP. And then another point, another difference is that we avoid explicit ports to remap behavior tree action directly at runtime. We only allow this remapping in some system configuration phases. And another difference is that we use push and pull semantic to know which behavioral specification must be executed. So this is a schema that I can use, I can describe shortly to explain essentially to make the link with what I was saying before about composite skills. So we have the task plan sequencer at the highest level, which is in charge of getting a task description in form of a behavior tree, a complex task, which is any complex task that you want to execute. And let's suppose that at a certain point in this complex task, there is a move to skill that must be executed. Okay. So, and this move to skill involves a specific robot, because in your setup you have two robots, a Franca arm and a UR10 arm, that both expose the follow path skill that allows the robot arm to follow a path previously computed by a digital twin. So we know which robot has to execute the task, and we know also which object we want to move to. So the point is that so first, what I was saying about pull and push semantics, to know which behavioral specification has to be executed. In the move to composite skill, the way in which this is implemented in nav2 with the navigate to pose, for example, the behavior tree is passed as an argument in the action goal. What we found more interesting was to enable this pull or push semantics to let the composite skill to interact with the knowledge base, which we suppose it knows at any instant what is the most appropriate policy that implements the move to that must be executed. Because why I say that the knowledge base knows at any instant which is the most appropriate policy to be applied to realize a move to. Because maybe we imagine that there are additional modules in this architecture, and these modules are about situation awareness. So situation awareness are modules that based on the current state of the environment and some inference capability can determine, for example, what is the most appropriate policy for doing a move to in a particular context. So a simple one without recovery, for example, in case your robot is just moving in an empty room and there is no much obstacles, and so we do not expect to be to have to do some recovery very often or things like that. But it can be, of course, different if the environment where the robot is moving is more dynamic or with a lot of obstacles. So depending on the changes of the environment and the inference that some situational awareness component can do, we can imagine that it's going to populate the knowledge base that can be accessed at runtime from the composite skill to know which policy has to be executed. So this can be done with a pool semantics like the one implemented here. So the move to skill receive the goal request, and it goes to in the goal handle. It goes to query the knowledge base to know which policy must be executed, and then continue with the execution. For example, here we have a compute path which is only bound to a digital twin. So okay, no problem. But there is also a follow path which yes.
We are running a little bit out of time. How many more slides do you have?
Okay, so I can speed up a little bit with this part, and yeah, okay. How many minutes do I have? Yeah.
-5.
Okay, no worry. I can do it. Yeah, so we use the robot identifier to decide to identify which remapping has to be done at runtime. But this is a remapping that was configured in the configuration phase before. So in this case, as I said, we have the pool semantics, but we can imagine also that the situational awareness component has communicated to the sent to the ROS node of the composite skill, which is the policy, and in this case we call that a push semantic, so that there is no more need of this interaction with the knowledge base for the composite skill. So this was a little bit about the timing. Don't go into the detail, but just to say that, for example, the goal request move to in the handle goal phase was connecting to the knowledge base interface and get back the policy to be executed. This is a pool semantic. Is a pool semantic. Otherwise, this part is skipped if the situational awareness component has sent already to the composite skill the policy to be executed. Okay, so that's all for the architecture. What we did was indeed implementing this architecture and using it in scenarios like assembly. Here we see in simulation a task with the Roboton challenge, with the setup from the Roboton challenge, and we use a flexible deployment and the rapid and effective management of software dependency thanks to the Docker visualization technology. So we deploy all this infrastructure with Docker, and then we program this also with the Papyrus for Robotics, so that is our low-code programming environment for these skills. So given that I'm a bit out of time, I avoid to give a short demonstration of the tool, but here is just to mention the main features. So the tool implements the Robosis methodology. Robosis was the project where also PTCPP has been developed and essentially pushed for the adoption of a model-driven approach in the development of software for robotics. So the basic features are modular role-based design. So we have views, different views for different roles to enable stakeholders in the robotics value chain to exchange model artifacts from which code generation can be done, but also some kind of analysis. We offer some preliminary capabilities of functional analysis, for example. And yeah, there are some links here with some videos to see the platform in action. So I go fast here. And what about our ongoing work? We are integrating in our architecture the part related to task planning to bring in deliberation capabilities. So again, from planning domains and specification of the planning problems, we have task planning integrated that can provide plan that is translating to a behavior tree that again is executed by the architecture that I described before. And then we are working very much on this part, which is called anchoring, and it closes the gap between the geometrical information in the digital twin provided by captors, sensors, like vision and so on, and the construction of symbolic predicates that can be used by task planner to plan. I think that's all. There is this video to show you our preliminary result of integrating PlanSys2 in our architecture with a preliminary anchoring capability. So we are working to make it more robust, more scalable, and implemented on top of ontology. So just to tell that the goal state was different here from, of course, the initial state, and the robot has to arrange the cube in a certain way to free one position. Then you see here the automated translation to a behavior tree from a task plan, and the robot afterwards moves the cube to achieve the goal. So that's all on my side. This was the last slide. I didn't have the time, unfortunately, to give a short demonstration of the tool. Maybe another time, the low-code tool that we developed, maybe for another time, if it's pertinent. But the main message that I wanted to share with you with this talk is that I think many of the participants to this working group have needs like the one I described at the beginning. So moving generic robots, agents in a skill-based approach. And it would be great if we could have a common architecture not embedded in a framework like, for example, Navigation 2, which is what they developed is great, but what I wanted to stress out here is that many things are really generic and could be took out of Navigation 2 to create a framework that could be reused in other contexts without too much dependencies and with also some improvement from an architectural point of view, as I said before, using the appropriate patterns from behavior tree C++ for sharing parameters and so on, the usage of this distributed knowledge base and so on. So that's all on my side. If you have questions, I will be happy to answer.
Thank you very much, Matteo. I think we have time for one short question, but then we also have some other things to discuss before 5. Maybe, is there, I mean, you mentioned on a slide that there's the need for a separate runtime for behavior trees, right? Is this part of Squidly, or what is Squidly?
Yeah, well, I mean, yes, the runtime for the moment is part of the full architecture that we call Squidly, and this architecture I didn't describe in its globality. I mean, there are other components that I didn't describe, like a situation awareness component and so on. I mostly focus for this talk on what I thought it was interesting for this working group. Essentially, the part of behavior execution. For now, we implemented it based on behavior trees using behavior tree CPP. It could be done also using state machines like SMAC. This is something that we are going to test very soon. Composite skill can be a composition of the different formalism. So we are open to bring this part out of our architecture because this is indeed very much inspired from the work in NAV2. And this is a basic, in our opinion, element, a basic asset, very much needed that could help the adoption of even more of behavior trees or other kind of behavior specification in an easier way if we don't put this in a single framework and then we have to all the time to clean up this. So the point is that when we started with the project that I described in the motivation sections, we found that what was in Navigation 2 was closely what we needed, but was not completely the right way to do it. We had some different ideas. So we wanted to isolate that part to be able to build around it all the components that we needed. And we think that this experience could be shared, and if there is enough interest, we can end up in a shared effort inside this working group to bring this development in open source and in an agreed way. Because I think that many other partners have this somehow, because I think MoveIt, for example, MoveIt Pro is capable of executing behavior trees. If we look at other frameworks like Isaac Cortex, for example. So I think that at a certain point, it would be nice to have a common agreed solution from which everyone can start. Maybe, I don't know. So this was something that I also wanted to bring to the discussion.
Yes, yeah, thank you very much. I think this is a very valid idea, and one step that we took towards the direction, or what I had in mind towards the direction would be that we, as a working group, first maybe understand what we mean if we say behavior trees, and therefore I created this rep. I'm not, to be honest, I'm not 100% sure if a rep is even the right format, but let's try this for now. So for those of you that have not had a chance to look at it, I guess I could briefly show the document, and if there are other, and then we have also like the video also opened the pull request already. Thank you very much for that. And then I guess if there are further questions, please feel free to reach out. This is under this GitHub organization ROS working group deliberation, and that's just a fork of the rep of the ROS rep repository. And basically, it goes into the first a bit of an overview of behavior trees. One thing that's maybe also new is this halt signal that we have to specify. I could think that maybe we need to do some more to specify this further, but then, for example, here under execution notes, you will find that what a halt signal does. That's something that's usually not found in the literature, but as you can see from behaviortree.cpp, this is necessary when you work with robots. Then basically, one of the core things is this table where we actually compare how these controllers are called in this book by Michele, how they are called in the library, and how we then propose to use the name, which basically means that we there's no sequence node per se, but there's basically a reactive sequence and a sequence of memory node that we differentiate against so that we are always sure what we mean. And then these controllers are explained in a graphical syntax and then with a pseudocode that details the actual internal workings of these controllers. I would personally still prefer if we had some kind of code here that is actually executable, but so that we could actually like test given implementations of behavior trees against this behavior. But I still don't have like a real good practical idea how to achieve this. So for now, we stick with this pseudocode where you would have to manually match this with a given implementation to see if it's doing what's said here. Davide, you raised a hand. You want to say?
Correct. So first of all, thanks a lot for putting the work to write this. So it's kind of convenient for me to jump in when you do most of the work. So thanks a lot. So first a very pragmatic suggestion. If you could enable in the GitHub repo the discussion, I think it would be easiest place to exchange opinions because there's no other. We don't have issues. We only have pull request activated. So that's a tiny suggestion to make future communication a little bit easier. So then so since we don't have that, I created this PR where basically I point out mostly to have a place where we can start exchanging opinions. So my problem is in the way here the sequence or with memory. They say that the sequence with memory is equivalent to sequence in behavior tree. In the top, if you go on the top on the comparison table, yeah. So the second line. Second line and further. I strongly disagree with this statement, and actually, the pseudocode kind of that is used is actually not correct. It doesn't represent what behavior tree CPP does. So I would like to maybe start this discussion because what we see there, the pseudocode we see there is not what behavior tree CPP does. And I've been looking at the publication from Michele, and I insist that the discrepancy that is mentioned in the table is not correct. It doesn't exist. So what he calls sequence with memory is sequence with memory in BV3 CPP. So that's my point of discussion before finalizing this document. So to correct this. And as you said, I completely agree with you that having real code and not pseudocode would be better, because the devil is in the details. So I think that the pseudocode is giving some, doesn't define something. For example, where you have the mouse, this to tick from last iteration, that's ambiguous, because what is that value when you started the first time? So there are these. So since the devil is in the details, and we are trying to really formalize, and also what you suggest, that creating some kind of unit test, I love that. I believe is what we should do. So I completely agree with you that maybe real code would be more effective here.
Yeah, but I don't really know a good way of, because to really then verify that when we have some executable code, to really compare this to a given implementation, we would have to have a lot of insight into this given implementation as well. Of course, we could make some kind of black box around the given behavior tree implementation with ROS, basically. But
if it's a unit test, why do you need ROS at all? There's no need to do ROS.
I want to be agnostic to the language, I think.
Cannot be agnostic. It can be agnostic to anything else but the language. So even if it's Java or Python, I don't care, but it must be a language, otherwise you cannot execute.
But we cannot make a unit test for that's language agnostic.
But when I mention unit test, it's more like giving a certain input, you deterministically get a certain output, right? So if we have a table of the input, for example, given 5 consecutive tick, you get this final result, and of course we don't even need the blackboard here. There's no use of the blackboard really here in this pseudocode. So I know it's not trivial, but I think it would be beneficial. Otherwise, we need to triple check this pseudocode to see if there is any error. And I believe right now there is unintentionally, there are some omissions that are important to fix.
So what would you be your suggestion to make this executable?
If we decide that is, as I said, a Python, C++, or whatever language, it would be easier to create an hello world example of what I have in mind. Otherwise, I wouldn't know where to start.
If we do it in one language, I would ideally want to be able to check this against an implementation in a different language where that does the same thing, right?
Yeah. The usual trick to avoid being is using inter-process communication. That is the most neutral way to make something communicate with something else when they are written in different languages. But what is it? But maybe it's just a table, a table like a text of inputs, and then you have a text of outputs, and then you just need the file IO, really.
Yeah. I was
That's actually, if you think about it, these coding challenges that are, that are sometimes used. That's what they do, right? They said, oh, your inputs, parse your input from this file, txt file, and then they check and then print your output on the console, and then they check if the output you print is the expected value. So yeah, I think that file IO with the inputs and outputs would be the best way to do that.
And inputs here are what are the states of the children in every iteration, right? And outputs are what actions are ticked. I think.
Yeah, it should be something like this. It's something like we have maybe some kind of test child. They say, oh, you always return success, or you need to return success. You need to fail 3 times and then return success. So you have this kind of hard-coded this sequence of return values, and that express the what that child node will do. And
Yeah, you're right. I mean, we need not only detect actions, we also need the return value of the whole of the subtree we are considering, or this control node.
yeah, the child are mock like mock testing, and what we are testing it is, for example, here is the controller. So we have mock child that has a certain deterministic output, and we are checking that given a certain I don't know, success, failure, then the control return failure or whatever, if that's a sequence. So as I said, the language agnostic way is probably file IO. And I'm happy to do, to try to create some kind of hello world of how this could look like. But anyway, we're going a little bit too fast. So I will say, thanks, Enrico. I see you there. Thanks a lot for working on this. Let's continue the discussion on GitHub and try to at least finalize the current pseudocode there.
Yeah, Enrico, do you wanna?
Yeah. So I wanted to, first of all, to thank you, Davide, for looking at the at the document and for your feedback. That's very useful, and indeed you are absolutely right. The pseudocode for nodes with memory is wrong. There is no doubt that the tooltick should be reset before returning success, for example, in the case of the sequence. So my understanding is that the difference between in the terminology of behavior tree.cpp, the difference between a sequence and a sequence with memory is what do we do, is whether we reset the tooltick, that we either we reset the memory in case of failure.
Correct.
And the sequence, we do reset it, and the sequence with memory, we do not. Is that correct?
Yes, it's correct.
Okay, that's great. So regarding the table at the beginning, I think it is a matter of terminology. So I understood from my main source on Michele's work is his book, and from the description of nodes with memory in his book, I understood that the memory was to be reset even in case of failure. So that's why I compared, like there is this comparison in yes, that one at the beginning. So of course I might have misunderstood it, and in that case this has to be adjusted. So thank you for pointing this out. And yes, let's keep the conversation going on GitHub, and hopefully to fix all these issues with the document. Thank you very much.
Yeah, then thank you very much for the feedback, everyone. In case anyone is interested, we are still looking for someone who would, like, I can still give a presentation slot to someone for the next meeting, but we could also extend this discussion, I guess, into the next meeting. No problem. There's also one raised hand from Calvin. We cannot see you now, but hi. We can't really hear you. No. Okay, no, sorry. Okay. No. Good, but I think we are anyways in the end, towards the end of the meeting. If there's a question towards anyone, then just send us a message, Calvin, or we can talk next time, okay? Yo. With discussion, Davide, you mean that there's a separate tab up here, right? Or you mean issues?
Yeah, if you go to settings, it's pretty easy. In settings, you'll see if you scroll down here, there's
This
discussion.
one.
You just need to activate. That's done. Save, and we're done.
I probably don't have to save, but they are here.
So this is like a forum. So I think that is the equivalent of a forum. That's it. See, easy peasy. So if there is anything, so we use PR for actual PR, and we use this for any. Hey guys, what do you think about this? Blah blah.
Do you then maybe you want to your pull request? Then maybe we just merge a pull request, especially for the.
You know what? I'm going to change the pull request just to contain the grammatical errors
This would make sense.
and nothing else, and then the discussion will be moved in discussions.
Okay. So Calvin wrote that the question was how to contribute. Yeah, I think using these discussions is a good way. I mean, if you have something that's a clear, for example, a typo, a clear correction, then feel free to open a pull request. And for everything that's worth talking about, then I guess we use these discussions. And then if there's a discussion already on your topic, feel free to contribute or otherwise open a new one. Yeah. Cool. Then have a nice week, everyone.
Yeah, you too.
Thank you. Thank you for the presentation.
Bye.
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 Thank you. Bye.
Bye.